All right, welcome to the PhD dissertation defense for Sahil Bhola. So he's going to be defending his PhD in aerospace engineering and scientific computing. It's been an incredible pleasure working with Sahil over the years. He came to University of Michigan as a JN Tata Scholar, which is a very competitive scholarship for all of India and highly selective. So he had some research experience before he came to Michigan. And then during his master's, he worked with Eric Johnson, and they did some very good work that was eventually published in the Journal of Fluid Mechanics. He also did an internship at Oregon, and he started doing a little bit of research with me on reduced order models. And in that period, you made, I think, a big advance, in my opinion. And so he started his PhD in CAS Lab in 2021, and over the past 5 years, he's worked on a wide range of things. Normally, I'd like to say very nice things about students, but I must say this is one of the worst possible combinations of advice to student, because both of us are extremely excited about everything, and we just want to get to the basics and work on everything. And that's really what he did. Any problem that was thrown at him, he would break it down completely, go down to the basics at the atomistic level, and then build things up. So it's been a great pleasure. And today he's going to be talking about part of what he did for his PhD. And the way we're going to run this session is Sahil will roughly present for about 45 minutes. And in those 45 minutes, if you have a question, he said he's going to pause 2 or 3 times, maybe 3 or 4 times. And if you have a quick question, feel free to ask, right? Nobody has this listening capacity for 45 minutes. So feel free to ask a question when he prompts. And then there'll be an open session. Anyone can ask questions. And then we'll have a closed session. Okay. With that, floor is yours.
Great. Thanks, Karthik. Thanks for the great introduction. So thanks everyone for joining in and making it. So today I'm going to be talking some of the work that I did during my PhD on reliable predictive modeling under the constraints of data, fidelity, and hardware. So let's dive right in. Yeah. So in applications across science and engineering, we have relied on computational predictive models to understand, design, and predict complex physical systems. So like ranging from satellite navigation to re-entry vehicle. Now, at the heart of these predictive models lies a solution operator G, which takes in an input, for example, the geometry, a parameter, a physical parameter such as the flow conditions, and maps it to a solution space which is of interest, such as the pressure around a vehicle. So to understand the physical processes and design physical systems, we need to accurately characterize the solution operator. But if you look at these systems a bit more closely, these systems typically have multiple sources of uncertainty. So for example, if you'd consider a re-entry vehicle on the right mode, it might face uncertainties due to unknown parameters such as inaccurate material properties at all times or inaccurate environmental conditions known at all times. So not only is the challenge that we must accurately develop these predictive models, but we must do so while accounting for these multiple sources of uncertainties. So if you look at the spectrum of predictive models, on one end, you have low fidelity models that typically utilize less total resources in terms of data, fidelity, and hardware. Now, these models are typically less accurate. For example, a RAN simulation is unable to accurately capture a lot of flow features. On the other end, if we were to invest more in resources, we might get like high fidelity models such as a DNS, which can capture more features. But if you look at practical settings, there's a resource constraint. So this might emerge due to factors such as making decisions in a constrained time or not being able to afford experiments, or you might not even have like a budget for computational resources. So not only we must develop these predictive models that account for uncertainties, but also must do so in a resource constrained manner.
Can you like click on that OK so that it's fine?
It's not here.
I think
You should put your mouse. Your mouse is here.
Yeah, put the mouse and click OK.
Yeah. Okay. So let's take a look at some of the practical resource bottlenecks that arise in predictive modeling. So first we have the data bottleneck. So you might not be able to acquire high quality data or it might be scarce or corrupted with noises. So this affects the training of predictive models and the characterization of the uncertainty. We also have a fidelity bottleneck where large high fidelity simulations which require fine spatiotemporal scales or this detailed description of the physics, which are typically a gold standard, but are also expensive. So any application that relies on multiple simulations of these high fidelity models can become very expensive in practice. So even if we have the data or like the simulator through a high fidelity model, there is this hardware bottleneck. This arises because of the limitations due to the memory footprint or arithmetic throughput. Now, modern hardware addresses this using low precision arithmetic, but low precision arithmetic introduces rounding errors, which can sacrifice the model accuracy and reliability. So let's see the impact of these constraints on the forward and the backward or the inverse problem in practical predictive modeling. So you might have some uncertain parameters in a predictive model, and you have a statistical model that depends on these parameters. Now you might propagate this uncertainty forward into the quantity of interest. This is called the forward UQ problem. And because of these multiple bottlenecks, some interesting challenges surface. Because of the data bottleneck, you might not be able to accurately characterize the uncertainty in the underlying parameters. And as a result, if you propagate that uncertainty forward, you might not be able to reliably estimate or obtain statistics of uncertainty in the quantity of interest. So because of the fidelity bottleneck, if a statistical model is implemented in high fidelity, it's typically very expensive. And if we rely on low fidelity models, there's this model form error, which would sacrifice the propagation of uncertainty, and the model form error itself or the uncertainty would propagate to the quantity of interest. For the hardware bottleneck, the presence of rounding errors corrupt the statistical model itself and its accuracy, and thereby, if you would propagate this uncertainty forward, that corruption gets propagated towards the quantity of interest. Now we can go the other way around. Given the observations, intend to try to characterize the uncertainty in the parameters. So this is the inverse problem or the inverse UQ. So again, because of the data bottleneck, here we might not be able to estimate or characterize the uncertain parameters well. And this might be because of the limited data or the corrupted measurements. For the fidelity bottleneck, if the statistical model itself is very expensive, doing inverse UQ becomes very expensive because it typically requires multiple evaluations of a high fidelity model. Now, in this case, even if you were to use low fidelity models directly, then the model form error or the inaccuracy would then be propagated towards the uncertain parameters. Now, the hardware bottleneck here does the same thing about like by corrupting the statistical model. And if we were to just rely on low precision arithmetic, then the uncertainty introduced or like induced in the uncertain parameters would also be corrupted by the uncertainty induced by the hardware itself, or basically the floating point errors. Now, looking at these different challenges in this talk, I'll talk about first a specific question within the data bottleneck, how we can determine what can be reliably estimated given the observations, or what can be reliably estimated under multiple sources of uncertainty. To address this, we developed a Bayesian identifiability framework that seeks to find which parameters can be estimated reliably before collecting the data in an entirely model-based form. So for the fidelity bottleneck, we seek to reduce the dependence on high fidelity simulations and basically see if you can't rely on high fidelity simulations, how can you develop predictive models that accurately characterize the uncertainty? Here we develop a probabilistic operator framework that can leverage low fidelity information in order to reduce the dependence on high fidelity statistical models. And this predictive model was developed in a resolution generalizable manner so that at inference time, you can query the model at any given discretization. So for the hardware bottleneck, we asked the question, how can we safely and reliably leverage low precision arithmetic? So to address this question, we developed a probabilistic framework that can characterize the rounding errors as random variables and rigorously quantify what's the uncertainty induced by rounding errors. Now, we also develop a probabilistic generative modeling framework which seeks to computationally efficiently propagate this uncertainty forward into the quantity of interest. So in today's talk, like I'll be mostly focusing on the fidelity and the hardware bottleneck. And based off of these contributions, these are the following publications, but I'll just focus on a limited one. So let's dive into the first contribution. So if you look at the present landscape, we have some statistical models that can characterize the uncertainty, and there are statistical models that are deterministic and thereby cannot characterize the uncertainty by the model framework. Now, the models that can scale well typically require large amounts of high-fidelity data and therefore become very expensive. So there is this ideal region we would want to head, and let's see what are the challenges that we face if you want to head in that direction. The first is any statistical model or surrogate framework right now, which is scalable, is purely deterministic. So as a result, if the underlying solution operator itself has some underlying uncertainty, it cannot capture that. So deterministic models can only capture the mean behavior and would ignore the entire distribution of solutions itself. The second bottleneck or the second challenge is the high fidelity simulation. So any scalable model, if you want to develop in a reliable fashion, it depends on high fidelity data. So let's see how we can address the first challenge. So first we'll start with a very simple finite dimensional view where we say the solution operator maps from a discrete input to discrete output. To characterize the entire distribution of solutions, we can develop an approximate distribution, a band price approximate distribution. But learning this directly in high dimensional is very expensive. So instead, we can start from a simple distribution and learn the map characterized with this vector field F and obtain an induced conditional probability path which seeks to approximate the target conditional distribution. Now, if we knew this vector field F, which characterizes this transformation, we can leverage flow matching framework, which seeks to learn a vector field H, which is typically like a neural network, and it regresses against the target conditional vector field. Now, the challenge is you don't even know what the target conditional vector field is. So the key idea is we can decompose the conditional probability path using a mixture of much more simpler paths. So these simpler paths are basically the conditional latent probability paths. Now, if we use this sort of marginalization, we can express the target conditional vector field using a latent target conditional latent vector field. And I'm just skipping the derivation, but this is something which we obtain. Now, if we express the target conditional vector field using a target conditional latent vector field, we can obtain a tractable learning objective in terms of the target conditional latent vector field. So in essence, what have we done is instead of first directly learning a conditional probability path, we first express this using a conditional latent probability path, which can be designed using, let's say, Gaussians. So instead of directly transporting the samples from a prior distribution pi of W to an induced conditional probability path, we seek to first express the conditional probability path in terms of the conditional latent probability path and transport the samples from a prior to the target by regressing against this conditional latent path. So in a sense, if we minimize this loss function right over here, we can still learn a vector field, a neural network, which can seek to learn an approximate distribution Q of tau, which approximates the data distribution itself. Now, there is a challenge right now. We started with a finite dimensional setting, but the issue with working with a finite dimensional setting is you can only query at locations where you train the model. So physics itself, like operators map, or the in physics, we have operators, solution operators that map between infinite dimensional function spaces. So an operator learning framework more accurately characterizes this map by learning a map between infinite dimensional function spaces. Now, let's see how we can lift this flow matching framework into an operator view. So the key idea is instead of expressing the finite or the vector field F as a map between finite dimensional spaces, we model it as an operator which would map between infinite dimensional spaces. Now, what this changes is, it's basically the same simplified diagram from a finite dimension, but what changed is now we characterize the distribution of functions in the prior space using a Gaussian process, and then map it forward using the vector field operator, capital F. Now, what this gives is you still have a loss function similar to the finite dimensional setting, but now you would have a loss that depends on the vector field operator F. Now, what in essence you obtain is by expressing things in an operator view, you can query your vector field and thereby your solution at any given resolution and any given solution domain point. Now, let's look at the second challenge, how we can address the high-fidelity simulation requirement. Now, in physical simulations, we typically have a low-fidelity approximation to the high fidelity, which is much more inexpensive. And the key idea here is, instead of directly learning this high-fidelity solution, what if we learn the residual between the low fidelity and the high fidelity? So in this case, we can construct a low fidelity as a deterministic approximation, and thereby the residual itself still would be stochastic because the high fidelity operator is stochastic. Now, the idea is, given an input A to the solution operator, we can first evaluate the low fidelity and then sample the residual using a learned distribution. Now, how can we learn this distribution? We can still leverage the operator view and learn this residual in a operator framework. What we get is that in addition to the input function space, we now have access to the low fidelity information. So given an input, you first query what the low fidelity solution is, and then they get what the residual distribution looks like. So this framework development was in 3 phases. The flow matching framework gives it the capability to characterize the uncertainty. The operator view enables resolution generalizable inference. And by learning in a residual space, we can actually leverage low fidelity information, which typically provides a good approximation for the high fidelity data or the high fidelity operator.
Sahil,
Yeah.
can you go back 2 slides? This one. So what is the relation between those 2 pictures? Is it just scale or resolution, or is it you did something else?
So it's just the same, like you have some input condition and run, like you have a known input condition, let's say, and the relation is just you solve it using a high fidelity. That's just for illustration that you solve it using a high fidelity. We solve it using a low fidelity.
Because here I'm making, when I see the picture, that means something else to me, right? And it's not just resolution.
It's not resolution. It's the reliability of the solution. That's why the right one, the intended illustration is the right one would represent something which is inexpensive but can still like capture some sort of statistics, and the left one is something which is very expensive but is much more accurate.
Fair enough.
So I have a quick
So-
question.
Yeah.
Are you focused on single fidelity or multi-fidelity is something that you will address later?
Yeah, right now we just leverage it's a bi-fidelity sort of framework, and multi-fidelity would be future.
Okay, thanks.
Yeah, fine. So the key idea here in the operator framework was to design a vector field that is an operator and can now leverage low fidelity information as well as input. So you don't have to look at the architecture, but the key features are we leverage feature-wise linear modulation of film layers to introduce some conditional information and leverage FNO, Fourier neural operators, spectral layers that can capture global features. So the second part is something which enables the operator formulation itself. So let's look at what's the advantage of the low fidelity inductive bias for the Darcy flow problem. The Darcy flow problem characterizes the pressure field given a permeability field. Now, we can solve this problem first by considering a baseline observed permeability field A, and then we can construct an unobserved stochastic high fidelity permeability field K. So the key idea is what you observe is something different than what's actually going on in the model itself. So the high fidelity solution would now map between the stochastic permeability field and obtain a pressure Whereas the low fidelity solution first is solved on a coarser grid and also maps between only a deterministic input permeability field to a low fidelity like approximation for the pressure. Now, in this case, the low fidelity evaluation is roughly 60 times cheaper compared to the high fidelity, but clearly ignores a lot of features and the uncertainty in the solution. So let's see what the framework enables. So we consider two different regimes, a low data regime and a high data regime. And on the top, colored ones for both the figures denotes the mean prediction, and the red ones are the uncertainty or the variance fields. Now you can see in both the data regimes, the low or the high data regime, introducing low fidelity information not only improves the mean prediction in the low data regime, but also can capture the uncertainty which is inherently present in the solution operator itself. And if we go to a high data regime, this sort of trade-off becomes less apparent, but what we get is super resolution. Since we did everything in an operator formulation, now you can perform
Sahil,
super resolution.
can I ask a quick question?
Yes.
I don't know if you're pointing to the screen. Unfortunately, I can't see it visually, but what are we supposed to be looking at to see that it's accurate and not accurate?
Oh, it's a qualitative one, but so the top ones is basically the mean prediction. And so in the low data regime, a lot of flow features, it's maybe like a bit harder to see on the big screen, but so if you see the high fidelity, you have some flow features here, right? So this contour line, but in the low fidelity, you won't be able to capture it. If you consider the deterministic approximations, the residual formulation actually improves the mean prediction a bit well. So that's on the mean prediction side. For the uncertainty, it's the bottom one, these red ones. So this is the actual uncertainty present in the high fidelity operator, which the model intends to capture using the generative framework. The FLORA, which does not consider low fidelity information, is not able to characterize this uncertainty. So you see like these multiple regions. So it intends to capture the variance as well.
Thank you.
The floral framework, which leverages low fidelity, it can capture these regions pretty well. But if you go to high fidelity data regime, leveraging on high fidelity data, you can actually get similar prediction, similar performance. Does that answer your question?
Yes, thank you for walking through that. Yep.
But in the high data regime, what we get is because of the operator formulation, you can perform super resolution and map between and train the model at a much more coarser resolution, but at inference time, or when you want to query it, you can query it at a much higher resolution. So in this case, you have a 8 times inference time super resolution, where the model was trained on a grid of 8 by 8, but inferred at 64 by 64. And here we saw just leveraging low fidelity information gives it additional guidance to improve the mean prediction and uncertainty characterization. When we test the framework across different solution operators, we see across different training samples, just leveraging low fidelity information helps. So so you have the floral framework, which leverages low fidelity information, and you have a corresponding residual FNO, which also considers low fidelity information, but is deterministic. Now, since these deterministic models cannot capture any uncertainty, there is no mean variance error. But if you look at it, the leveraging low fidelity information actually improves the mean variance error, specifically in the low data regime. To summarize, we developed a probabilistic operator learning framework that combines 3 things. First, it can leverage low fidelity information. Second, it can inherently capture the uncertainty because of the formulation itself, so you don't need any post-hoc surgery. And the third is it can give you resolution, inference time resolution generalizability. So we started with this landscape on the rightmost, and the idea was to move and come towards this star where we intended to reduce the requirement on high fidelity data and still remain scalable. So before I move to the next part, are there any pressing questions?
How exactly is cost measured between the different methods? Is it just the availability of data, or
there are multiple things. So it's basically hardware utility. Now, how much was the wall clock time, training time, etc., and accuracy. It's multiple features were considered. Yeah.
Yeah, I have a couple questions. So in the broad view, when you talk about fidelity bottleneck and data bottleneck, I kind of want to clarify the relationship between the two. Does like more fidelity immediately lead to a data bottleneck, or is data bottleneck you're only in isolation thinking about events that happen rarely or things you cannot observe very well, right?
So there's an overlap between the two. Like if you look at the Venn diagram, so in this case, this bottleneck, what I just mean by the fidelity one is you don't want to perform high fidelity simulations to train your predictive model. So there, it sort of falls in that overlap itself where you are getting data from high fidelity simulations. But more broadly, the data bottlenecks represents that you can't just acquire data. So a lot of applications getting experimental data or getting observations for solving the reliable inverse problem becomes very expensive. So there's that overlap. So there's the sort of in that overlap.
Okay.
Yeah.
Also, so maybe it was somewhere in your slides already, but you mentioned estimating like parameters of Gaussians, but a lot of the diagrams you had seem to have multiple means and modes to them. So I was wondering if there's a reason why using a single multimodal Gaussian works.
Yeah, it's actually a good question. So that was not really. So in this figure, the key idea is, okay, you have a multimodal distribution. So that's the dotted red one. You are expressing that as a mixture of Gaussians. So these Gaussians are centered around the data points. And so Gaussians are just easier to transport. You have closed form expressions. You can just think of the data, it's being centered around these data points. And you're expressing a distribution as a combination, as like, it's more like an empirical distribution that you get once you observe, once you get data.
Okay, cool. And my last question for now is
when you hold until the end, these are excellent. Okay, these are good questions.
When you're doing like flow matching in like an infinite operator space, I imagine that has to have some constraint for it. So I was thinking like, it's like, oh, all this stuff has to be like linear in between there. Do you think that would be helpful at all, or is this flow like somehow completely outside of that range, and
there are
much more free space to it?
Good question. There are limitations for sure. Like for example, I leveraged the Fourier neural operator. So this depends on the Fourier transform. So easily, like all the limitations of Fourier transform gets here, and at some point you have to truncate the distribution or the transformation, so you won't be able to capture a lot of high frequency features. So that itself is a challenge. So covering like having flow problems where you have very high frequency features, that would definitely be a challenge. So there are like pros and cons to it, but yeah.
I see, that makes a lot of sense.
Thank you. Questions coming, but these are very good questions. But yeah, keep going.
Okay, so let's look at the second bottleneck, the hardware bottleneck, and how we can develop reliable statistical models when we want to leverage low precision arithmetic. So traditionally, scientific computations have relied on high precision arithmetic for reliability. But this becomes a challenge as problems become larger and larger because of a large memory footprint and the cost of performing arithmetic operations using high precision arithmetic. Modern hardware provides support for low precision arithmetic, which is much more compact in terms of the bit layout and is much more efficient. So you can reduce the memory overhead and get gains in computational efficiency. Now, why can't we just blindly use low precision arithmetic? So first, let's take a look at the floating point numbers, which are basically a subset of real numbers. So as we decrease the precision, we can not only represent less numbers, but the spacing between the numbers becomes coarser and coarser as the numbers become larger. So representing any number using a floating point representation then introduces a rounding operation and a rounding error, and this error grows as you decrease the precision. So the key idea is we need to
Your scale on the x-axis for those numbers, it goes between 1 and 4.
Yeah.
If that plot is between minus 100 million and plus 100 million, will that plot look the same?
No. Yeah, so you can imagine it as like a comb, and the spacing changes like so much. So so that's one of the reasons people do normalization. It's much more stable at low precision arithmetic. And the reason is you can't express very large numbers. It will just overflow. Yeah. So the idea is we need to quantify what's the effect of rounding errors. So there are two approaches, a backward error analysis and a forward error analysis. So a forward error analysis basically studies what's the effect of rounding errors in the output space. And so you study what's the accumulation of rounding error and see how does the computed value y differ from the true value. Alternatively, backward error analysis tends to find or seeks to find the smallest input perturbation delta x, such that if you would use a perturbed input x plus delta x and evaluate it using the true operator, then you would end up at the solution y hat. So in practice, to study forward or backward error analysis, we seek bounds for the backward or the forward error. To develop these bounds, we need to model the rounding operation. And for IEEE arithmetic, this is given by a computed value is basically the true value, and you have this rounding error term. The rounding error term or this delta value is actually bounded by what's called a unit roundoff, and it's a machine specification. Now, a trivial way to just quantify the error would be just consider the worst case at every step, but this dramatically overestimates the accumulated uncertainty or the accumulated error, and it's an unreliable way to estimate the error. The key issue with such a deterministic approach is it does not account for cancellation of rounding errors that happen during successive computations. Now, how can we first just take a look at how the rounding error sort of behaves? Across arithmetic operations, we can make two observations. First, we don't always hit the worst case scenario. So rounding errors can be somewhere in between. And the second is a rounding error at the current step can influence and can result in cancellation in rounding at a later step. So this motivates a probabilistic formulation where we model the rounding errors as a random variable and then view the problem as the uncertainty induced by the floating point arithmetic. Now, if we perform such an analysis on a computational kernel, you actually get product of these rounding error terms, which is modeled using a 1 plus theta n, where n is the number of operations. Now, the key idea is we can bound this accumulation using the Bernstein's concentration inequality by taking logs on each side and seeking bounds on this sum of random variables. Now, the proof has 3 steps. The first step is we can we can leverage Bernstein's concentration inequality with the random variable zi, which is just the log of 1 plus this rounding error term. The second is we can specify a required confidence zeta and then solve the quadratic on the right-hand side for the variable t. The third is we can use the positive valid root of this quadratic and bound the Sn term. Now, following these 3 steps, you get this theorem. Please don't read it. Now, there are theorem assumptions and some theorem features. The theorem assumption is we started with like an IEEE model, and we also assume independent and identically distributed random variables. The theorem features are we did not make any specific assumptions about the statistic of the rounding error random variable, and we can therefore utilize any or plug any rounding error distribution into this theorem. The third is we get a favorable square root of n dependence, which is often observed in practice and is not captured by the worst case deterministic setting. Since we can model the rounding error random variables, we can account for the distributions which are obtained in practice. For example, if you were to add a very large number to a very small number, the rounding error distribution actually gets biased towards negative value. That's the distribution on the left side. Now, we specifically consider 2 parameterizations for the rounding error distribution, a U model and a beta model. A U model implicitly enforces a zero mean assumption by modeling the rounding error as a uniform distribution between negative unit roundoff and unit roundoff. A beta model leverages a beta distribution to account for bias. Now, the key idea is by accounting for bias, we can model the true accumulation of rounding error. That's the figure on the right. And as you can see, the beta model can actually capture that depth compared to the U model. Now, let's look at some experiments. For the dot product case, when we have data which is distributed between 0 and 1, and you can have some sort of bias in the rounding errors, you see any model which would assume a classical zero mean, would be unable to capture the true backward error, and a beta model can capture that growth. If we were to consider the data distribution between -1 and 1, all the models don't perform well. The reason is because in addition to the cancellation of rounding errors, there's actually cancellation of the data itself, and none of these models account for that. And if we were to account for that, then we would need to make additional assumptions. The next, we look at a matrix market case where we picked up roughly 700 matrices from real practical scenarios spanning from CFD, chemical simulation, circuit design, etc. The idea is we pick a matrix A and we want to evaluate the uncertainty induced in performing matrix vector multiplication AX, where X is randomly sampled. Now, in this case, you see, if we were to just consider a worst case deterministic bound, the bounds just fail for FP16. And if we were in a less sparse region where the matrix has a lot of entries, all the bounds perform fairly well. Now, these bounds perform they are a bit more conservative as there's much more sparsity, because the model, these underlying, does not account for any specific assumptions about how the data is distributed within the matrix A. So to summarize, in this case, we developed a probabilistic rounding error framework that can be used to quantify the accumulation of rounding uncertainty. And this model is general enough that you can plug and play any rounding error distribution as long as it's bounded. And the key idea is we can get the square root of n dependence and address the limitation of the deterministic worst case bounds. Now, before I go ahead, are there any questions? Yeah.
Okay, if I heard correctly, did you just mention that like it does work for any kind of quantization error, right? So if I use like fixed point and threw away floating points for whatever reason, you would like everything would still fit in very nicely.
It's IEEE. So the theorem assumption was IEEE arithmetic.
Wait, what like special bound does that? If you could like briefly summarize it.
So the arithmetic model, if the computed value is true value times 1 plus delta, that's a fundamental modeling assumption, and that is true for IEEE arithmetic. If you were to extend this to quantizations, that model needs to be updated, and we need to address that.
Okay, so it's the quantization, not just in the encoding, but also in the operating and how you.
Yeah. How you perform, how you express these arithmetic operations itself. Yeah.
Gotcha. So the other thing is when you were analyzing the matrices, like a good chunk of numerical analysis is like spectral analysis and error of like really small eigenvalues. I was wondering, so if you're doing all this error analysis, or is this like a situation where you actually just care about the numerical values of the matrix and how you multiply rather than the spectrum of those matrices?
Yeah, the idea was you have matrix multiplications in practice solving these systems, or like you have matrix vector multiplication. The idea was not just to first we limited the condition numbers of those matrices, which we picked. So it was not to analyze the properties of the matrix. Rather, if we were to use that matrix and perform the multiplication, right? One thing which I did do was make sure the matrices, if I were to multiply, they were stable and it did not overflow. So that was, but the key assumption or the key motivation was to just understand how matrix multiplication or matrix vector multiplication would, how much error would it generate in terms of floating point.
Okay, next.
Any other quick questions? All right, keep going.
Okay, so so far what we have looked is how we can develop backward error bounds. So that was in the input space. And if you look at practical engineering and scientific applications, we typically need what's the effect of rounding errors in the output space. That's basically the forward error. So the key question is, if you have multiple sources of uncertainty typically present, then how can we propagate the uncertainty from the backward or the input space to the output space in an efficient manner? So this work would basically bring things together from aspects from generative modeling and numerical analysis. So let's start with what the backward error actually does. When we do a backward error analysis, what we get is an effective input x tilde, which is the observed input, the input that you actually wanted the model to compute. And we get an input perturbation delta x. Now this delta x is bounded by the backward error bounds, which you get by the numerical analysis. Now in theory, for linear operators, you can quantify what's the effect of what's the forward error bound, like here, but this just propagates the worst case input perturbation to the worst case forward error. The second is, if we were to quantify this, you would need to evaluate what the function phi is, which is typically implemented in the highest possible precision and can get computationally expensive. Now, the key idea here is we can model the input perturbation delta x as a random variable with distribution informed by the known input and what the machine information is, which is characterized by the unit round of u. So under this assumption, the effective input is actually a random variable itself, and now is informed by the unit round of u and the known input. Now, what you have effectively translated the problem to is, now that if there is an effective input, let's push it forward through the true operator phi and quantify the uncertainty. So there's some uncertainty in the input x tilde, and we push it forward through the computed or through the true operator, this phi, which is implemented in the highest precision. Now, if we were to do this, there's a limiting case. The limiting case is if you were to choose a unit round off of 0, that means you have infinite precision, right? Then the perturbation, the input perturbation would collapse to a delta distribution, and what you would end up getting is the true computation itself, and you would just propagate the uncertainty due to the input and not due to the floating point errors. What this gives is now you can change the machine specification, the unit round off, and query the push forward at any arbitrary precision. So you can basically change the size of this box, which is characterized by the unit round off. So if you would typically have a low precision, this box would be larger and the resulting uncertainty might look different. Now, the issue is if the input itself, x, is uncertain and you are simultaneously propagating the floating point uncertainty, then evaluating this phi operation multiple times becomes very expensive, right? So the key idea is, how can we leverage flow matching and inform it by the numerical analysis, the backward error bounds, and propagate this uncertainty due to floating point error? So we can design a flow matching vector field, which is now informed by a gamma scale, which characterizes the backward error bounds and obtained by numerical analysis and the known input x. Now, the key idea is the flow matching framework intends to learn what is the push forward or what's the uncertainty in the output distribution, this phi and push forward with the x tilde, the effective input. Now, the idea is we can amortize the cost of pushing the uncertainty due to the input x as well as the floating point uncertainty at the same time. So we consider a special case of solving a linear system where ax equals to b, A is a symmetric positive definite matrix. And through numerical analysis, what we actually get is a perturbation on the input matrix A. And this actually gives us what the gamma scale is, and will be utilized by the conditional flow matching framework rather than the full matrix delta A, which would be very expensive to condition upon. Now, this gamma scale inherently specifies what the machine unit round or the unit round off is, the machine precision, and therefore you can condition at any given precision. Now, let's look at solving a pairwise symmetric positive definite linear matrix linear system. Ax equals to b, where A is pairwise by a low dimensional parameter theta and is constructed using a fixed orthonormal basis, and b is a fixed right hand side. So if we look at the data distribution, when we query at any given precision, and we see that increasing the precision reduces the uncertainty in the prediction, and that's sort of intuitive. Now, the idea is, or the goal is, given an input parameter theta and arbitrary precision, can we get the computed solution and characterize the uncertainty in the computed solution? So these are some results. So we had a precision 8, just having an 8 bits or 18 bits. And you can see the prediction somewhat reasonably captures the the spread of the computed solution. That's in the blue ones. Now, since we condition the model using a precision, we can at inference time query it at any given precision. So the model never saw double precision arithmetic, and you can actually query the model at any given precision. So in this case, you see like the difference between an 18-bit and a 53-bit is not so significant, which sort of gives an intuition to the model that you can solve that system at a lower precision arithmetic without sacrificing the accuracy. Now, if we look at some unseen cases, combinations of the input parameters theta and precision, and if we query the model using high precision, like high double precision arithmetic, we see there's actually an improvement in the the predictive accuracy. So what this framework enables us is, given an input A, arbitrary precision, what is the uncertainty in the output and what's the prediction? And rather than relying on the expensive operator phi, you have amortized the cost. So here's a quick contribution summary for some of the work I've done. So the data bottleneck, which I did not really talk today, I focus on the fidelity and the hardware bottleneck. So the fidelity bottleneck, actually, we developed a probabilistic operator learning framework, which seeks to reduce the dependence on high fidelity computational simulations by leveraging low fidelity information. It can exploit the fact that the vector field in the flow matching framework is an operator, and therefore at inference time provide resolution generalizability. And we saw that it actually improved when we leveraged low fidelity information. For the hardware bottleneck, we developed a confidence calibrated rounding error analysis that seeks to quantify what's the effect of rounding errors rigorously without making any big O truncations. And this framework can then be utilized to study different systems. I showed a quick analysis for the Cholesky factorization, solving a linear system by Cholesky factorization, and then showed how everything kind of comes in together, the fidelity bottleneck and the hardware bottleneck, and work in that highlighted the overlap region by developing a conditional flow matching framework that is informed by the machine precision. So some key insights that emerged from these studies was the modern generative modeling framework provides enough flexibility that we can sort of mirror some classical modeling approaches such as pro-critic, and it can simultaneously propagate the uncertainty and capture some real physical systems which are inherently stochastic by modeling them as random variables. The second one was where we developed the rigorous, we did the rigorous rounding error analysis, and what we obtained is by modeling rounding errors as random variables, we can get the favorable square root of independence and extend beyond the classical zero mean assumption. So now you can actually just utilize it. You can go back, you can study your system, you can get a rounding error distribution and just study what's the effect in the quantity of interest. The third is where we brought things together in terms of numerical analysis and generative model. And the idea was, how can we amortize the cost of propagating the uncertainty when the inputs are uncertain and we want to evaluate the model at any given precision. So what this gives us, it's a modeler's tool where you can, at decision time, see if I want to use low precision arithmetic. So you can compare it if I actually need a high precision hardware, or I can just use a low precision model. So some high-level future works. So the first framework actually did a bifidelity, and I think Ahmed asked. So that one of the key things was we can extend it to a multi-fidelity framework where you can have different combinations of low-fidelity models and combine information. And a probabilistic generative model can sort of seek to combine these different sources of information. Second, the low fidelity information must provide some sort of information, useful information about the high fidelity. And when it actually performs well, we need to carefully study that. The second is the precision aware scientific machine learning. So instead of just sacrificing the physics, you can sacrifice the numerical accuracy to develop low fidelity models. So you can develop low computational fidelity models rather than low physical fidelity models. And we can, by doing rounding error analysis, we can actually study the behavior of rounding errors and capture what the realistic accumulation of rounding errors is, but by first characterizing the rounding errors as random variables in your specific application and using like a similar sort of analysis. The third is basically a scalable, reliability aware uncertainty quantification, where we can look at large scale applications. So the third, where I brought everything together, it's somewhat still small scale, but in large scale simulations, you might need to make a decision if I want to operate with mixed precision or a single precision. And this sort of modeling framework gives you enough flexibility by first doing a numerical stability analysis and then studying what sort of precision choices I need to make. So these are some of the publications that like emerged over the past couple of years. I did talk about a few, but okay. So good stuff. Okay. Over the past couple of years, I've it's been a really long journey, and I have a lot of people to thank too. I want to start with Karthik. Thanks so much for accepting my application, PhD application after me emailing you I don't know how many times. But yeah, thanks for taking the chance and giving me the opportunity to chase random ideas and go in I don't know, random depths. And yeah, thank you for believing and giving me the space to grow. It really means a lot to me. And yeah, thanks for sending me to Rio right before this. I got so much coffee and pushed through. I was able to push through this because of really good coffee. So thank you. And thanks, McD, for sponsoring this. I want to thank my committee members. Yeah, thank you for reviewing the work. And yeah, I really appreciate all the feedback and you guys had.
The last part was purely because of the committee feedback from the pre-defense.
Yeah, yeah. So the last part, specifically bringing things together, actually it was, thanks Claude Code. Yeah. So yeah, bringing everything together. Thanks for the pre-defense comments and everything. Thanks, Ahmed, for the amazing internship opportunity. It gave me so much insights and flexibility to expand my horizon. Beyond serving on my committee, these members have offered amazing graduate level courses, and all the growth has been in so many ways part of these graduate level courses that I've had the opportunity during my master's and during my PhD. Yeah, a lot of my research directions evolved. I came in during my PhD or master's, I'm gonna do CFT. It changed. So yeah, people ask me, this is not CFT. So yeah. Yeah, over the past, during master's and undergrad, I have a lot of gratitude for my collaborators. I've had excellent mentors and collaborators. I've had the opportunity to learn from these people and grow. I was able to expand my horizons, work on these different topics just because of these people. Specifically, I want to thank Tapan Singh Gupta for giving me the opportunity to start my research journey in such an incredible way. I had zero experience, so I really have a lot to owe him. So yeah, I'm really appreciative for all the collaborators that I've had. Thanks so much. For CAS Lab, I'm very proud to call myself a fellow CAS Labber. Yeah, it's been a very long 5 years, but I've had incredible time. I've been part of CAS Lab, so many lab outings, getting drenched at Cedar Point, but still wanna skip the Thursday meeting to go to a ride. And it's been an incredible time. I want to thank Jasmine, helping me all the way towards from my prelims exam when it was sprung to me in a month's time, I think. Yeah, and I really want to thank her and thanks for finally making me move upstairs. The view is definitely better.
There's six alums on the call.
Oh,
and
that's great.
Elnas is here as well, so 7.
Yeah, I'm really glad for the time I've had at the lab, and it's been precious. So thank you all. So it's been a long journey, and it would not have been possible without like the amazing friends that I've had, like all the way from my undergrad to my master's and during my PhD. Like the PhD journey is a very long journey and it can get very challenging, but I'm glad to have had like the support, specifically like with the downs, with the ups, when the presentation's not ready 2 days before the defense. So all of that, like I've had so much fun, and this journey was just made special because of the incredible time like I've had with you guys. And yeah, I'll look forward to making new memories. I want to thank my partner Srishti for so many things. Um, it's been a very incredible journey, but super challenging. And she has seen like the ups, the lows. She has been through she has been through all of these moments together, and I'm incredibly grateful for the support she has had to she has offered. Not only like celebrating the great times, but like um, going through all the lows together. And I'm really thankful for all the support you had together. Thanks, Vishnu. To my family, yeah, it's like coming for the PhD. I don't know, how you guys like send me over like solo, and I just like visited you for a couple of I guess once over the past years. But I'm really glad for your support, and this thesis or like this dissertation is just possible because of the love, support like I've gotten from you guys. And I'm so glad like during all the lows I had like our house pets like Storm and Caesar to just entertain me with so much fun. I'm really glad. So thank you so much, and it's all for you guys. So with that, I'd just like to thank you, and if you have any questions.
Sahil, I have a quick question. The acknowledgement that you made is fantastic. Is this like customary part at the university, or this is something that you did? Because it's one of the good things I've seen so far.
Thanks, Anand.
So I want you to ask very, very good questions, but hold them for a little bit because you had a few. But I want you to ask. I don't want to shut you down. I don't know who you are, but you ask me.
Yeah, maybe I can go then. Yeah, so first of all, a wonderful talk. I had a couple of questions.
Yeah.
So in the first part of your talk, where you talked about the learning, where you use the data from the low fidelity to like inform your learning as well.
Yeah.
Sorry, can you like give a brief comment as to how much less data you will require if you were also to provide the low fidelity data for the same level of error metric?
Okay, so for the same level of, so we didn't do like that sort of rigorous analysis where we fixed the budget, but the idea was okay, actually, let me rephrase that. The idea was if you were to fix the trainings, epochs, like fix the hardware, fix all of these different things, just by adding low fidelity information, what helps? Like in terms of the data, the number of data points itself, we didn't do like a scaling there, and find an optimal trade-off.
Okay.
But the idea was that, okay, if you fix the training budget, I'll just want to train it for 300 epochs or something.
Okay.
Can I improve, right? If my data generation is expensive or just running the model, it's expensive, then can I get improvements there?
Oh, okay.
That was the
Good. Makes sense. And in the last part of your talk, you did this, you had this AX equal to B solving, and you used that. So what was the size of the matrices you used there for A?
Oh, that was illustrations, 20 by 20.
20 by 20. Okay, okay. And okay, can you go back to the slide?
Yeah, let me. This one? Or
yes, no, the next one. Yes. So here you show for different bits, right? So my question is, let's say if I were to plot this some error metric for as a function of the number of bits, can you give what will that shape look like? Like logarithmic, linear, or how will it look?
That's a good question. Like that's something I didn't really take a look at. I think like it might flatten after a bit. Like it's not like continuously just increasing the bits like help, because in case like if you notice 18 bits and 53, it doesn't really change a lot.
Right.
Right. In the Abel norm, it does not. So I think like it might decrease like for a bit.
So you're saying it'll rapidly decrease initially and then like stagnate.
Just like plateau out.
The question is, Would you expect some kind of log, or what do you expect?
I'll say maybe the intuition says like it's going to be rapid than linear, but I'm not sure if it would be logarithmic.
Okay.
Yeah, that's what the intuition says. Yeah, but that would be interesting to look at, like finding that cutoff and developing some scaling relations there.
Nice.
Yeah.
And I have this question. I don't know if it's even a logical question, but in this finite bits, you have this matrix and exponent, right? So if you have to play with the number of such bits, will it affect these results?
Yes.
Okay.
Yeah. It will actually, so it will be, so the unit round off,
Right.
that's informed by the base and the precision itself, right? So
Okay.
changing the base and the precision would change things. So this would not change with the exponent range.
But the mantis will affect that, right?
Yeah, the mantis would affect.
Okay. Sounds good. Thank you.
Other questions?
Where did that beat salad come from? It's really great.
Oh, thanks.
All right. Questions?
No, that was my question.
Oh, that was
yeah.
Great question.
I gotta know.
No, I mean, if anyone's silent for more than like 20 seconds,
Yeah.
you get to ask.
What would you need to do to extend the bifidelity framework to multifidelity?
Yeah, that's a good question. So right now, multiple things. For example, right now, we didn't look into if the models are like, okay, there was more like an empirical study of correlations, but then I feel we can use like some more extensions from control variates, where you have a telescopic sums. And then maybe if you were to able, I think you can condition the vector field on some sort of class, that this is the class of model that I have, and then learn a residual for that class. I think that's, so you can have that telescopic sum, right? The difference between these fidelity levels, and then you can query the vector field, I think, based on the difference that you want.
Right now, even the bias is linear, right? You're just like taking the low plus you're adding the residual.
Yeah.
So you can just do that like for many.
You can, yeah. So you can just, but yeah, if you have additional information, like you know what the exact like the correlations is, you can change that telescope, like you can have like an alpha parameter or learn it like based on the data samples or something. But yeah, you can, I think you can extend that. But that was a simple, like the most simple representation of correction. You can have multiplicative corrections and stuff there going on as well.
Other questions? Get you, I shut you down earlier.
No, just a question from before.
Okay.
I can ask later.
I have to shut him down.
So in the first part of your talk, where you learn this FNOs and stuff to do the learning.
Yeah.
So I have this question. So you are learning the operator, but the operator is still discretized in the, let's say if you use a 8x8 bit mesh or matrix or something.
Yeah.
So the operator is still discretized in that space.
Yeah.
So my question is, how is it extrapolating into a 64x64?
You first do okay, let's start with a simple case. Like, let's say you work with bases, right? So you extract some like global features, right? So let's say you have a discrete representation. You can instead like learn some global features as well, right? So that's what, so the Fourier neural operator, what it does is it works in a Fourier spaces, right?
Okay.
So there is obviously going to be an error, and this because of the Fourier transformation itself. So you can start with a discrete representation as well, but you can first do a Fourier transform. So that's the so you instead the modeling framework does like a linear transformation in a Fourier spaces.
Okay.
So that's the goal. So you learn some sort of basis functions.
Okay, and the Fourier basis is big enough in some sense to capture this.
Yeah, you do some sort of truncation there,
Sure.
and that you obviously have the Nyquist limit there as well. But the idea is that you learn some global features that are discretization independent.
Okay, so thank you.
Yeah.
Final questions?
Hey, Sahil, there are a couple questions on Zoom.
Oh, yes, please go ahead. Yeah.
Um,
Oh,
Did you
I can read it out if you want.
So stochastic rounding is fundamentally different. Punch. So basically, stochastic rounding, you are making a decision in which direction you are rounding, and overall, that's a choice of the rounding operation that we use. In this case, it's round to nearest. The rounding operation itself is linear. It's deterministic, but you're modeling the rounding errors as probabilistic. So the justification of this is because it's not just the rounding error at a current step. These rounding errors interact with each other in a very complex manner. And you might observe, this is more like an observability, non-observability sort of thing. But you might not observe the rounding errors at each step. You will have to run a different simulation and you can't evaluate like, the combinations. But it's a bit different. Stochastic rounding, it does provide much more stable results for a lot of cases. But we did focus on the deterministic modes and then model rounding errors as probabilistic. For temporal integration, that's a good question. We did have some results for ODEs. For time-based simulations, the rounding error actually grows, and then you have to like unravel each of the time steps. That's something we didn't take a look at, but it's a very complex error growth, and that's something we didn't look at it yet. The
Unit scaling on slide 45 in the yellow box. You probably want to go to slide 45.
Yeah. Okay. So
once you can just read the question out.
List of data, will that work?
Once feel free to ask the question.
Yeah. Hey, Sal,
Yeah.
thanks for the first part. It was pretty informative. I was just asking if your method can account for this high range situation where you have a couple of elements in the matrix that are at, let's say, 1,000,000 value, and then most of your data is centered around 0 or very low range value. So how do you account for that kind of a bias?
Yeah,
if at all?
that's a good question. So for the matrix market case, let's say I explain it using that. This is an a priori example. So you don't specifically assume how the data is distributed. But if you were to assume how the data is distributed, you might leverage some different concentration inequalities. Like you can leverage martingales, and there's some work out there where people make the additional assumption for the data itself. And we didn't do that. We just assumed the rounding errors are random variables and didn't extend it to that. But extending this work to where you assume some data distribution, I think, yeah, that's an interesting direction. But there are works based on martingales, like concentration inequalities, which do that. Yeah.
Thanks for answering. This is great stuff. Thanks.
Okay, thank you. I think we need to close the open part for lack of time. But yeah, thank you for engaging, and thank you for all the cast. Any questions? Grab a few pizza slices as you go. The committee members, I want to ask what your cutoff is. Run like that or
3:15.
Oh, 3:15. Okay, yes. I was suddenly panicking.
Oh, actually, 3:30 should also be.
Okay, I thought we were already at 3. Shane and Alex, are you free?
I'm good on my side.
Yep. Okay. Ahmed, do you have any constraints?
No, I'm okay.
Okay, great. I'm gonna stop recording.